Hi everyone, thank you for attending this webinar dedicated today to pedestrian wind comfort and safety guidelines in Canada with UrbaWind. So let's move to the next slide. Today, that will be a joint webinar with SLR Consulting with Shannon Testart. So myself, I'm Guillaume Cagnot, urban climatology expert since almost 15 years and technical manager of the urban product line at Methodin. And Shannon.
Hello, everyone. I'm Shannon. I work at SLR Consulting Canada. I've been an UrbaWind user since 2013, so a long time now, and I'm very happy to be joining Guillaume for this webinar. Thanks, everyone.
Thanks a lot, Shannon. So let's move to the next slide. So of course, you can ask us any question during this webinar. You have a chat panel on the right side. So we will answer to all your questions. If we don't have time, we will send you an email that sum up all the question. And you are all mute, so we can carry on. So this is the contents of today. We will deal with pedestrian wind comfort criteria, go through guidelines for Canada, understand the influence of master plan on comfort mappings. I will talk specifically with our in-house product called UrbaWind, a CFD tool dedicated to assess pedestrian wind comforts. And I will let the floor to Shannon with the projects she has been leading with UrbaWind. And at the end, we have a question time. And I forgot to mention that we will send you this PPT, of course, for those who have been registered. Okay, so let's move to the next slide. We start with a quick word about Methodin. So Methodin exists since 22 years today. We are software developers and experts around wind engineering. We develop CFD software, CFD for computational fluid dynamics. And we provide different wind expertise from wind energy to urban world, transportation, and we have a new department now with climate change. So on the next slide, I will talk to you about also quick word about our service. So we propose a tailor-made weather climate service. We have more than 700 earning studies that we have done here. So here we are. And on the next slide, I just want to show you where we are. We are in Nantes, in the certain points. This is our headquarters. We have one office in India and 2 offices in China. Okay, so let's start by a topic of today, the pedestrian wind comfort. So what is the wind? The wind is air motion that induces force on the bodies. This also can be a concern for safety pedestrian. The boundary layer that depends on the land cover, the topography, and also depends on aerodynamical interaction. So this is the topic of today. The wind in urban area are strongly different from those nearby meteorological station because of topographical effects. So the question is how to design the master plan. So let's move to the next slide. Let's talk about the criteria. I would like to talk to you also that about hypothesis. We do not talk today about Wind chill, humidity, solar radiation, clothing. We talk about only mechanical wind comfort. We will have a dedicated session for that at the end of the year, related to a thermal indicator called the PETs that we are intended to develop. Wind comfort assessments of urban projects is common practice in most wind engineering team nowadays. So how is it done? It can be assessed through this methodology. We need to define what is the wind speed threshold and the frequency of exceedance of this threshold related to pedestrian activities. It depends on pedestrian activities and depends on the country rules. So on the next slide, I will talk about now about aerodynamic. Let's talk about the turbulence wind, which is a three-dimensional random process. Here we have a record of the wind speed versus time. It's raw data, and you can see how fluctuated is the signal. And this is what we call turbulence. The wind speed actually can be derived along three components. We have the main component along x, which is u, and two orthogonal components, v and w. On the next slide, I would like to show you that it's a random process. So you see that before. So to handle that situation, we prefer to talk with statistics. So we derive the wind speed with the mean parts. So we have u bar, v bar, and w bar, plus the fluctuating parts, small u, small v, and small w. And these fluctuating parts can be described through statistic with turbulence intensity, which is ui, is equal to standard deviation of the wind speed divided by u bar. So we will deal only with u bar and turbulence intensity. So from three complex quantities, u, v, w, we will keep only two, u bar and eu. On the next slide, we will see how to compute the wind comfort. So first we need to define the gust speed. The gust speed is equal to mean part, u bar, t, plus a part that reflects the turbulence with the coefficient alpha. On the graph below, you see the record of raw data, very turbulent. We add the mean parts, which is u bar t, and we have also the gust velocity. And we see that it is superior, it can be also equal. So how to compute it? Well, it depends of your application. Is it wind comfort or wind safety? In all cases, you will have a mean part, which is average over a time sample. This time sample t range from 10 minutes to 1 hour. It depends of the country. Sorry, for France it is 10 minutes. For Netherlands it's 1 hour. And then we have a coefficient also depends of the application and the country. So it range from 0 to 4. So with 0, you keep only the mean parts. For example, in France it's 1. In Canada, we see that later it can be 3, and other country it can be up to 3.6. So the range is quite high. There is an alternative way that is used in UK or former UK country. It's called the gust equivalent mean. So what is it? It's a combination of the mean speed and the gust speed, and we are taking the max between the mean speed and gust speed divided by 1.85. So it's a good ratio. When you have turbulence density can be very important in complex area, whereas turbulence intensity is low in countryside. So let's see on the next slide how to characterize the wind comfort. Let's talk about categories and activities. The wind comfort criteria are based on the frequency of wind speed threshold exceedance and on the pedestrian activities. Here we have an example with Lawson criteria. It is based on wind speed in Beaufort's force. There is an equivalence between these two measurements, and it stands from 0 to 8. And it's expressed in function of the percentage of time exceeded of this criteria, wind speed criteria. For example, if you want a comfortable activity like sitting on a terrace, you have an image on the top left. You want less than 1% of the time higher than 3 meters per second, which is 1% over a year, which is about 3 days in a row. Or for running, for example, this should happen less than 6% of the time with wind speed higher than 5 meters per second. So you have different kind of activities. You have some example on the left on the image. Okay. On the next slide, here are the guidelines for Canada. I would like to focus on that today. So I've split the table in two groups for Montreal and other cities. For Montreal, the actually criteria depend of the season. It range for 4.1 meter per second to 6.1 meter per second. And they are looking at the mean parts. It means that alpha equal to 0 for wind comfort, where for wind safety, it is alpha equals to 2, and the event are for wind speed higher than 20 meters per second. For other cities, for Toronto or Hamilton, alpha equal to 3, which is quite a high value, and the wind speed criteria is 5.5 meters per second. If you are looking at the safety now issue, here alpha equal to 2, and we are looking to very high events of 20 meter, 5 meter per second. For events about 0.1% of the time, so over a year that represents 9 hours. Very, very small amount of events. Okay, let's move to the next slide. I would like to show you how to assess the wind comfort. So first step is the wind that is recorded at the weather station is really different at your project because the weather station is characterized by high wind speed and low turbulence density, where at your project it's usually the opposite, low wind speed and high turbulence density. And also you have some aerodynamical effects. So I want to show that on the next slide. I made some comparison. I took the windrows at the reference station at 10 meter high. So you have prevailing wind coming from the east, and you have wind speed which is very small, not easy to look at. This is about 3.17 meters per second. It's written in very small character. So that's a reference station. Now let's have a look. I will extract some windrows in the pattern of the project. Let's have a look on the bottom right. So the prevailing wind is also coming from the east, so nothing changed. It's not disturbed, but we have less wind speed. There are more blue in the windrows than at the weather station because the wind speed have been decreased due to the land occupation. Okay, now if we go a little bit upper in the center part, we see that the on the windrows, everything is coming from the south part. The flow has been channeled by the buildings. And then in the upper right part, the wind flow is also coming from the south. And on the left top, you see that the flow is now coming from the east. So it's very, very complex to guess in advance how looks like the flow in the districts. So why that? On the next slide, I will show you three main effects. The most famous, I think, it's a Venturi effect. So it's a speed up between two buildings or a row of buildings. It is characterized by acceleration. So you see on the right part, you have red color on the picture. It means strong acceleration. And the discomfort is mainly due to those high winds. So this is the Venturi effect. On the next slide, I will show you what we call the corner effect. When you have tall buildings with downwashing flow from incoming wind, you will have a strong acceleration at the corner with a shear layer. It means that you have a red color, which is strong acceleration, and just next by you have blue color, which is very slow wind. So this will create a shear layer, and this creates a lot of turbulence. So this will be very uncomfortable area. Now on the next slide, I will show you the last one. It's called the Wise effect. It happens when you have two buildings in a row with a smaller building in the front, and you will have first a small vertex and upstream, and the bigger one just after. And moreover, there will be some kind of corner effect when the flow exits on the bottom right of the buildings. So this will bring a lot of turbulence, so a lot of problems. On the next slide, what's the reality is that you get some kind of mixture. For one direction, you can have three different effects on different place. You can have a Venturi, corner, and Wise effects. Now, for several wind directions at the same location, you can have a mixture of those effects. For example, you see on the picture, you have a strong red color for one direction. This could be a Venturi effect due to the tall buildings. Now, if the wind is coming from orthogonal direction, it can be a Wise effect, a downwashing effect. So you can imagine how complex it is. And of course, the discomfort is based on frequency of wind speed threshold exceedance. So what you need? You will need tools, of course, to deal with that. The first one is to run full-scale experiments. But this is very difficult to set up. You need a lot of data, 1 year of data, expensive and time consuming. So nobody do that. Next one is scaled down model. It's about century technology in wind tunnel. It's quite accurate, but it is expensive and time consuming. And the last one is CFD. It's about 50 years technology, and nowadays it's very reliable and very fast technology. Okay, on the next slide. So how do we carry a wind comfort? We will need a climatology data that can be statistical with a tab file, or can be temporal data with time series, with wind speed and wind direction. You will need to run several wind direction with your CFD tool because of different situation with aerodynamical effects, interaction. And then you can apply your wind speed criteria and compute the frequency of accidents. So on the next slide, I will focus on UrbaWind. How do we do? To set up the case, you will need buildings, which is mandatory, topography when it matters, and you can add porous elements to like trees or hedge to slow down the wind. Then you will run several wind direction. UrbaWind will create a mesh and solve the wind equation called the Navier-Stokes equation. User can define a boundary condition. Nearby is project. UrbaWind will post-process using weather data. And then you can set up wind comfort analysis with wind speed criteria and alpha coefficient and get a wind comfort mapping. On the next slide, how is it done? You will need obstacles in a format called STL. That will be for your building or vegetation and also topography. You will have also need weather data, which can be statistical or time series. Then you will run your case, and you can compute wind comfort. On the next slide, how to collect data, and this is very, very important because UrbaWind will be sensitive to the quality of your wind data as much as the quality of the CFD itself. So you can ask to your national weather data. You can go on with your free weather providers such as NOAA or EPW for Energy Plus weather data. And you can ask with Meteonorm also. There is another way, which is reanalysis. So we have developed that in Methodin. You can ask any point in the world, or you have other company can do that. On the next slide, a quick word. So how to build those data? You may need some conversions using Excel. So very straightforward. Only 2 columns for wind data, wind speed, and wind direction. EPW is quite straightforward. On the next slide, so you can fill in this. We have a dedicated page to the validation, so you can have information about our projects. And the next slide, and this will be my last word, is how fast is it? So depending on the complexity of your case, the computation can range from 5 minutes with simple case, or it can be up to a day, basically for one direction. But it depends also of your computational resource, and you can run on multiple CPU to get it faster. Okay, so let's move now to Shannon. You can present now. It's the floor is yours.
All right, thank you very much. Hi, everyone. I have a few case studies here to present. I see we're getting a bit short on time, so I will try to zoom through these. I just picked a few case studies that show kind of a variety of possibilities of what we can do with UrbaWind at SLR. And on the next slide, I'll demonstrate our standard type of analysis. So here, this is Waterloo Student Housing near the University of Waterloo. You can see in the top left there that it used to be 20 years ago, it was mostly all single detached houses. And now in the bottom left image, you see that it's all basically student apartment buildings, and then shown in Google Earth. And we did a lot of the wind studies for these. There are kind of very standard type of wind studies where we're doing something for a municipal planning application. So on the next slide, we'll look at a snapshot of the results for that. So the first image there is a SketchUp model. We use SketchUp for all of our modeling. It works quite well with UrbaWind because it can export those STL files that we need. And then that middle image is an example of the UrbaWind results that we get out of that for comfort. And then the third one is showing our comfort criteria. Those are our default criteria that we were using a lot more before the Ontario municipalities set their own criteria, which they've done a lot in the last 5 years. So it's switched to a lot of GEM criteria, but we were initially using a mean criteria, which is shown there. And on the next slide, I'll show another study where we look at wind flows. So this is an example where we did two different phases for the study because they built one expansion and then a second expansion separately. And we were looking at the wind flows around the building, which you can see there. That's showing the mean wind speed. And then there in Google Earth, we see the building completed, which is always cool. So on the next slide, we can look at the wind vectors. So here we're looking at the ground floor, like grade outside, wind flows around the building, and then also the wind flows around the rooftop of the building. And in this particular case, we were concerned with snow accumulation to make sure that they didn't have a high snow clearing need at grade, and then on the rooftop that the snow wouldn't interfere with the rooftop intake louvers, which are shown in the roof plan there. So on the next slide, we will discuss topography. So most of the time we build our UrbaWind topography as flat just because that's easy and simple and makes sense. But sometimes the topography is significant in a way that is definitely going to affect the local wind flows. So you can see in the Google Earth image there that we have quite a significant ravine around like two sides of that building. So then the bottom image shows the same model in SketchUp with the SketchUp terrain brought in. And then the third image is that same terrain brought into UrbaWind. So we use the SketchUp terrain directly in UrbaWind and it actually works quite well. And then on the next slide, we'll look at some rooftop amenity areas. So this particular developer, this is for a hotel in the States actually, they were very concerned about what the wind would be like in their rooftop amenity areas. So we tested a few different situations, particularly about what the parapet walls would be. So we tried solid parapet walls as well as porous walls. And it turned out that the solid walls blocked the most wind. So that's what we went with and what we show here. So you can see there's a rooftop amenity up at the height of that big tall tower, which you can see there's some fast ones up there. And then a more sheltered area on the podium, which is on top of the parking garage that you see in the middle of the building there. And then you can see the pool deck, which is kind of the back face of what we're seeing there. And we did achieve really good winds on the pool deck. So that was great news for the client. So then on the next slide, we will look at trees. So here, the two left images, you can see the difference that including vegetation can make in the results. So in that top one, we have quite bad acceleration at that corner, but then the trees really clear that up. And then there in UrbaWind, we can see all the little trees that we made, and then we see the built building with the mature trees in the park, and then the trees added along the street. And then on the next slide, we'll look at snow. So then we do some studies using UrbaWind for snow drifting in northern communities. So it can be quite bad. As you can see in that image there, the snow was piled right up to the doorway, blocking the doorway of that building, which obviously is not ideal. But the wind is very predictable in the north, what direction it's going to blow from. So we can do a lot to design the orientation of the buildings to have the wind help clear snow rather than cause drifts. And we'll see UrbaWind in use for that on the next slide. So here we're looking at the wind frequency above or below 6.6 meters per second, because that's about the wind speed where the wind is going to move snow around. So the purple areas with low wind speeds, you're going to expect snow deposition there. And then in the orange areas, you can expect the snow to be cleared. And then the vectors, we can look at like where we're going to have recirculation zones or where snow is going to be moving in and out. And then we can use vertical flows as well to understand wind flows above and around the building. And then on the next slide, we'll take a peek at a wind tunnel model. So as I was saying, we do a lot of municipal planning applications. That's the majority of what we do. So earlier on in the study, we'll do a CFD model. And then later on, it often moves to a wind tunnel model of the same site. So that's what we're seeing here. And it's just, I find it neat to see it kind of come to life in the for the wind tunnel model in foam and wood as we're seeing there. So that's kind of the progression of our studies. And I know that was a super lightning fast and I went a bit over. So apologies for that, everyone. But that's all I've got. I will pass it back to Guillaume.
Thanks, Shannon, for this presentation. Sorry for being so versatile. So it's time now for any question in the chat panel. We will be there for some times, 5-10 minutes, depending of your question. Very interesting presentation, Shannon, with the snow application. This is the first time I see this kind of application, so very interesting.
Thank you. Yeah, we have a lot of snow expertise in our team with Tarana Loveland, who's been working in snow for decades now. So we get a lot of northern snow work through that.
It's the kind of question we may ask in the ski resorts in France. This kind of consultancy, but that's not common practice, I would say, in France. Okay, we have a question, and I can answer to that question. This refers to the land occupation. If your building is nearby the coastline, how can we adjust that? Well, you have land occupation that you can adjust on the boundary layer. You can set up sea roughness, so this about 1 millimeter. And whenever you are close to the build-up area, you can set up to more roughness length, which is district or high density, from 0.2 to 0.8, depending of your country rule also. This can be set up in the software in the boundary condition. Okay, to carry on this discussion, this is also about to define the roughness. So you don't need to actually define the outer boundary condition. This will be difficult. So it's when you do that, you apply from the upstream condition what will be the right land occupation. If you have the sea on the west coast, so from some direction coming from the west, you apply roughness of the sea. Yeah, a few minutes left before we end this webinar. You can, of course, send us question anytime, at least to me and Shannon if she agree. But at least you can send it to me.
Yes, for sure. Feel free to reach out, anyone.
Okay, thanks a lot. Okay, so I don't see any more questions, so I think we will end this webinar. Very interesting, Shannon, your presentation. Sorry, I was too versatile, but I hope you you enjoy it, Shannon. Hope you enjoy also the attendees. You want to add something, Shannon?
No, I think that's good. People can definitely reach out if you have questions for me or my team. And yeah, we'll, as Guillaume said, we'll be setting around the slides so you can look at my pictures and notes if I sped through it too quickly.
Okay, okay, sounds good, sounds great.
Thanks.
So,
have a great day, everyone.
thanks a lot. Have a great day too, and let's tune. We have other webinar coming this year. We will communicate about that. So see you later. Bye bye.
Bye.